Hi, I'm Stevie C and the Place to Be. In this video, I'm hopefully going to be making something that BigClive hasn't made, and this is a set of neon relaxation oscillator fairy lights. Now, you'll recall that we've both made a set of these neon fairy lights, and we've both made neon relaxation oscillator light bulbs. So I thought I'd combine the two. So just like last time, I'm going to assemble a string of the neons in parallel. As you saw, I'm going to use the helping hands to help divert the heat away from the glass envelope, and I'm going to use one of these little plastic spacers that you can salvage from cheap LED fairy lights to help separate the leads of the neon. The only difference this time, you'll notice I've not used any resistors in here, and that's because all the current limiting is going to be done by the power supply I'm going to put together. So much like a string of LEDs, if I just poured this into the mains right now, they would pull as much current as they could until they destroyed themselves. So I've got to design a power supply. Now the power supply I'm going to use is very similar, if not identical, to the supply I used in the Neon Relaxation Oscillator test tube. So we've got a 470k resistor. This charges up this 10 nanofarad capacitor until one of the neons lights up. This will happen about 90 volts because that's the strike voltage of the neons. So the one neon that lights then pulls the voltage down to 50 volts. This is the neon hold voltage, which means obviously at this point no other neons can strike as the voltage isn't high enough. This diode in here then runs the circuit half wave by lopping off one half of the AC sine wave. So the neon stays lit for the remainder of that sine wave cycle. And then when the next sine wave cycle starts, the process repeats all over again, hopefully with a different neon lamp. And as BigClive pointed out, I'm using this 1k resistor in here to limit the degradation of the neon electrodes, which occurs due to the high voltage spikes that they're subjected to. Right, so this whole process took several attempts to get right, and I'm still not 100% on my technique, so just bear this in mind before leaving comments or whatever. So basically, I've designed the circuit and sprint layout. I've left myself two options for resistors. I can use a 470k or two 470ks, or I don't know, I'll work it out later. I've printed out the design onto silkscreen transparency film, just like I did with the Audio Wave Gobo project. I took a piece of single-sided copper clad FR4 fiberglass board, cleaned it and cut it to size. Next, I attached some of this dry film photoresist Next, I sandwiched the printed circuit board silkscreen up against the FR4 board with a plate of glass and exposed it to ultraviolet light with my nail curing gizmo. So now it's time to develop the board with a sodium carbonate decahydrate solution. Wherever the ultraviolet light has penetrated through the transparency film, it's changed the properties of the photoresist. You'll notice that I've inverted the colours on the printout so that the tracks are transparent, so the area I don't want is solid black. So where the light has been blocked by the ink, i.e. the area we don't want, the photoresist remains susceptible to being dissolved away by the sodium carbonate developer solution. Now, one thing of note, as I massage this, I can feel the difference between where there's just copper and where there's track. It's only a fraction of a millimeter, but the fact I can feel that probably means that it's developed enough. This will also help me when it comes to drilling, because the drill bit will be able to home in the void between where the photoresist remains. So to etch my board now, I'm going to put it into my solution of ferric chloride. So now that I've thoroughly made a mess of my workbench, I've submerged the board in ferric chloride to etch it. So what happens here is the copper on the FR4 board is going to be eaten away by the ferric chloride, but not in the places where the photoresist remains, i.e. where the tracks are. And I'm using the hot water from the developer stage to transfer heat into the ferric chloride to speed up this process. So after rinsing the PCB, I can drill it with 0.7 and 1mm tungsten carbide drill bits using a Dremel and a flexi shaft. So now it's time to clean my board with acetone and rinse it so I can solder in the components. So now it's time to populate the board with components. So that's us back in the wide shot and ready to test the light string now. So place your bets now. What's going to happen? Is it going to work as expected? Is it going to do nothing? Or is it going to go kablamo? We shall see. It's working. So there's one neon hogging the voltage, as you kind of expect, until the neons settle in a bit. But they are all trying, and it is sort of working as I expected, except for this one. Right, so obviously this light string operates at mains voltage, and I've no desire to touch that circuit board to prove it, so you'll just have to take my word for it. What I'm going to do is I'm going to use one of these little project box enclosure type things that I bought from eBay to contain the circuit board. So now that we're in the relative darkness, you'll see they're becoming a lot more active. I've got my original set of neon fairy lights in here just for comparison more than anything else. I would show you the watts and the amps and all the rest of it, but they just do not register, so no point. I'm noticing this one isn't lighting at all, so I'll probably go back and change that, and I quite want to add some more to it, to be honest. I want the string to be longer. So I've just hidden the circuit board away in this box. Once I'm probably finished, I'll drill the holes out and pot it properly, but just for the moment, it's good enough. So there you have it, my neon relaxation oscillator fairy lights. I genuinely didn't know if this would work, but I'm glad that it does. So, like, subscribe, leave suggestions for future videos, and I'll catch you next time. Thanks for watching.